Good morning, everybody. Thanks for joining today's webinar titled Distribution Resources Planning, Laying the Foundation for a Modern Grid. I'm Josh Valentine, Communications Manager for the Clean Coalition. Before we jump into today's presentation, just want to remind you of a few quick items. This webinar is being recorded and will be made available on the Clean Coalition website. A recording of today's presentation and the slides will be sent out within 48 hours after the webinar is completed. And at the end of the webinar, we will have time for a question and answer session. To ask a question, please go into the control panel of GoToWebinar and type in your question, and we'll try to get to it at the end of the webinar. With that, I'd like to introduce our speaker, John Bernhardt. He is the Outreach Director for the Clean Coalition.
All right. Thank you very much, Josh, for the introduction, and thanks to everybody on the line for taking the time to join this presentation today. Here's a quick overview of what we'll be covering. So first, we'll kick off with the discussion of how the electricity sector is changing and how those changes have created the need for enhanced distribution system planning. Then we'll dig into the details of what distribution resource planning is, its benefits, the steps leading states are taking, and then discuss how this key policy can be initiated in your state or utility service territory. So for those of you on the line not familiar with the Clean Coalition, we are a nonprofit. We were founded in 2009 and based in the San Francisco Bay Area. Our mission is to accelerate the transition to renewable energy and a modern grid, and we do that through technical, policy, and project development expertise. We have a couple focus areas that just kind of help shed a little light on the type of work that we do. So the first is analysis and planning. So understanding and investigating the full cost and value for distributed energy resources, or DER, which is a term that I'm sure many of you are familiar with and that I'll use regularly throughout this presentation. So just for clarity's sake, when I say DER, I'm referring to local renewables, as in distributed generation, energy storage, electric vehicles, demand response, as well as energy efficiency. Second, we do grid modeling and optimization, so power flow modeling of distribution grids to understand the characteristics of that grid and be able to put forth an optimal portfolio of DER. Program and policy design, that comes to distribution grid planning, procurement policies for distributed generation, other DER, as well as interconnection processes. And then lastly is design and implementation of community microgrid projects, which are complex substation level DER projects to achieve at least 25% of annual electric energy needs from a local substation area from local renewables sited within that same distribution grid area. And really, this is our vision for where the space is headed and where all of our work is pushing towards. Everything we do is to establish a cleaner, more reliable, and more resilient, as well as more affordable power system. And truly, this is the grid that's going to come to realization in the 21st century. In this 21st century, electric grid is going to be more distributed, it will be more integrated, and will also be more flexible. It's going to be operated in concert with DER on both the utility side and customer side of the meter to optimize value for all grid users. And it will be more resilient against both natural disasters, terrorist attacks, and human error. And the development of this 21st century grid is already underway. Investments are being made today and really every day that's going to influence the capabilities of this future grid. Which brings us to the need for distribution resources planning. So this slide may be reviewed for many of you. It's the basic structure of the US power grid and how the grid has been operated for many decades. Traditionally, there has been a one-way power flow on the grid starting at remote large-scale power plants, often thermal plants like coal, nuclear, and gas, but also increasingly from large wind and solar farms. The electricity from these centralized generators travels over high voltage transmission lines, and think those big metal power poles that you see in the middle of nowhere. They eventually hit a distribution substation, they get down converted to lower voltage, and then that same electricity is delivered to end-use customers through the distribution grid. And distribution grid, just think those wooden power poles in your neighborhood. But now the grid is truly at a strategic inflection point. Distributed energy resources like local renewables, energy storage, demand response, and energy efficiency are transforming how we generate, manage, and deliver electricity. Ultimately, these DER plus the monitoring, communications, and control systems that tie them together will work seamlessly to locally control and balance both supply and demand of electricity. And all of these transformative technologies are sited close to end-use customers, making distribution grids truly the center of innovation. So no longer will the grid be dominated by one-way power flow and vulnerable over-reliance on remote generation and transmission. It will be increasingly full of DER sited throughout communities where people live and work, and the grid must be able to manage local and bidirectional flows of power. And this transition that we're seeing is really being driven by a rapid drop in the cost of distributed energy resources. For years there has been overwhelming public support for solar and other renewable energy technologies. But now these technologies are increasingly cost competitive for both customers and for utilities. And both customers and utilities are investing in these resources. This shocks a lot of people, but solar beat out natural gas on price in Minnesota in 2014, which is seemingly like an increasingly long time ago. What we're looking at, this headline here, is from the Aurora Solar Project, which is a 100 megawatt distributed generation project that utilizes solar arrays ranging in size from 2 to 10 megawatts across Xcel Energy service territory in Minnesota. The arrays were located in 16 counties and all interconnect within multiple Xcel Energy substations and will provide energy and capacity for the local distribution network. And the fact that these resources are sited within the existing distribution grid was a major reason that they were so cost effective and able to beat natural gas on price. That's because they were able to avoid the long distance transmission of energy, which is both expensive and inefficient. So since this 2014 Minnesota example, costs have continued to decline dramatically, not just for solar, but for energy storage as well. So in early 2017, a Hawaii electric cooperative signed a deal for dispatchable solar power, which means solar on demand, even after the sun sets, for 11 cents a kilowatt hour. Now, just to put that in context, that's 1.9 cents a kilowatt hour cheaper than the US average residential electricity price. So what we're seeing is really substantial declines in the price of DER. And most recently, I'm sure some folks saw a lot of the headlines surrounding the results from Xcel Energy's 2016 Electric Resource Plan all-source solicitation in Colorado. These results have been described as shocking, among other things, but you can see here highlighted in red that wind alone came in for about $18 a megawatt hour, which is 1.8 cents a kilowatt hour. Solar alone came at 2.95 cents a kilowatt hour, and both of those paired with batteries are still exceedingly cheap and actually far cheaper than any other similar projects that have been seen to date. And I will note that these are the median prices. So this means that actually half the bids were lower than these prices and half were higher. So this truly is evidence of just the continued significant and precipitous decline in DER pricing that we're seeing, and renewable pricing that we're seeing. So all these projects and data points are evidence of a major transition currently underway across the US and the globe. As this graph illustrates, we've seen huge price declines in renewables like solar over the past 40 years, and there has been a corresponding rise in the deployment of these resources. So industry experts expect to see steady growth of solar PV across all US market segments of both large remote utility scale installations, as well as distributed solar generation. So as the economics of DER continue to become more favorable, we're going to continue to see increasingly rapid deployment of these technologies. So there's strong consensus that distribution grids are going to become increasingly the centers of innovation and investment, and really the focal point of grid modernization efforts across the country, because they already are showing themselves to be this. The EIA, the Energy Information Administration, reported that 3.5 gigawatts of small-scale solar capacity was installed in 2017 alone. And we're seeing upwards growth in storage, EVs, smart meters, demand response programs, and other advanced energy technologies. Yet all of this is happening in the context of there being far too little information, insight, and transparency into utility distribution networks. And they pretty much look like this for the most part. They're like a black box. And the old adage is true, is you can't effectively manage what you don't measure. And there's little chance that we can smartly modernize the grid if we aren't comprehensively measuring and assessing the grid. Therefore, there needs to be greater data transparency, insight, and planning focused on the distribution grid. Now, transformation of the power system is already underway and is only going to accelerate in pace. So the real question is, how painful will this transition be? Will it be well planned and cost effective, or will it be poorly designed, reactive, and unnecessarily expensive? Now, what we need to do to achieve that smart, thoughtful, cost-effective transition is really break open the black box that is the distribution grid. We need enhanced visibility and knowledge of the status and capabilities of existing distribution grids if we want to modernize the grid in a smart, thoughtful, and cost-effective way. And it's critical that we do understand both the capabilities as well as the limitations of existing distribution grids, and identify where opportunities are to best leverage this infrastructure. For example, where does distributed solar provide the most value to the grid? And conversely, where does new distributed solar provide the least value to the grid? And I think most people would agree, including politicians on both sides of the aisle, regulators, utilities, ratepayer protection advocates, electricity customers, and other interested stakeholders, that we should be striving to make the smartest possible investments into grid modernization. But we can only achieve this goal by proactively studying and analyzing the grid to guide our decision making. Now, this is where distribution resource planning comes in. Distribution resource planning, or DRP, as I'll call it, establishes a comprehensive and transparent framework designed to improve distribution system planning, operations, and investment. It seeks to optimize utilization of existing electricity grid assets and new DER resources to modernize the grid while minimizing costs for ratepayers. And in the Clean Coalition's view, distribution resource planning, or DRP, is a foundational policy for modernizing the grid to provide cleaner, more affordable, and more resilient power. So DRP, distribution resource planning, first launched in California, officially with legislation in 2013, and had a number of goals, which I think Pacific Gas and Electric has laid out very clearly. The first is to modernize distribution systems to accommodate expected DER growth and two-way flow of power. The second goal is to enable customer choice of new electric DER technologies and services. And the third is to identify and develop opportunities for DER to realize grid benefits. So the third question is asking, in essence, how can a utility leverage DER, whether on the customer side of the meter or on the utility side of the meter, in a way that maximizes value for all grid users? So on the customer side of this meter, this is really kind of alluding to the shift from consumers to prosumers and enabling customers to contribute services to the grid, whether it be from utilizing solar plus storage to load shift, to participating in a targeted demand response or energy efficiency program. And on the utility side of the meter, this type of process can enable utilities to spur the development either through direct ownership or through procurement of strategically sized DER at key locations on the grid. And I think there's one real good example that kind of sums up how resources on the utility side of the meter can really maximize and capture benefits for all grid users. So Long Island Power Authority they had a feed-in tariff program known as the Clean Solar Initiative, and it was designed to bring 150 megawatts of local solar online. So the utility, LIPO, realized it could utilize local solar to defer $84 million in planned transmission investments if it were able to bring 40 megawatts of that capacity, that solar capacity, online within a specific transmission grid constrained section of its service territory. So the utility designed an additional feature on its feed-in tariff that offered a locational premium of 7 cents a kilowatt hour on top of the base rate, which was about 16 cents a kilowatt hour, to all solar projects located at that critical point within the LIPA system. And the expected savings, even taking into account that 7 cent a kilowatt hour locational adder, was still projected to save ratepayers about $60 million, as opposed to needing to make that significant transmission investment. So, these goals that PG&E have laid out, I think these are great goals and something that I think every state and utility really wants to work towards. But they're big and daunting goals, and I think we need to talk about how the components of distribution resources planning can actually make meaningful progress towards these goals. So let's dig into the actual components of distribution resource planning. And in our minds, there's 4 key components. The first is hosting capacity analysis. Now, this is a proactive assessment of the existing distribution grid to understand at what locations capacity exists to accommodate new DER, which makes interconnection of these resources quicker and cheaper. And then grid maps with details on the available hosting capacity down to the circuit level are then made publicly available and regularly updated. The second component is a methodology to value DER. So this is a method determined through a stakeholder process to assess the full value of DER to the utility and to the grid, with recognition that the value will likely vary depending on the location of a resource. The third piece is substation level demonstration projects. So these projects proposed by utilities and approved by regulators will deploy DER to achieve immediate ratepayer savings when compared to conventional investments in centralized generation and more traditional pole and wire grid upgrades. And I think one thing that's useful about the demonstration projects is they actually put into practice those previous 2 steps of identifying opportunities on the grid through the hosting capacity analysis, and then employing and testing out that methodology to value DER. And then the last and final piece is DER forecast. So the grid is not static and it's perpetually changing. So utilities, as part of their distribution resource planning effort, should be creating various DER forecasts based on a number of scenarios. And these forecasts should include details on expected siting at the distribution substation level and the potential impacts this could have on distribution transmission planning. So thinking ahead, on that 10-year planning horizon, how could the growth of DER impact investments that the utility is considering making in that same time horizon? So let's take a little time and dig into each of these 4 components. So the hosting capacity analysis, and this is also known as the integration capacity analysis, that's what it's called in California. And I think probably everybody on this call, if you're familiar with energy space, knows there's a total abundance of acronyms. So the HCA, hosting capacity analysis, and ICA, I'm using those interchangeably. So the hosting capacity analysis determines the maximum amount of DER that can be accommodated at a given place and point in time under existing grid conditions and operations without adversely impacting safety, power quality, reliability, or any other operational criteria, and without requiring significant infrastructure upgrades. So this image that we're looking at details the type of information that a hosting capacity analysis uncovers. Now, this is from a small section of Southern California Edison's distribution system, with details on a specific line segment of its grid and its ability to handle both new local generation from sources like rooftop solar, as well as additional load. So it is projected that for this particular line segment, which is 12 kilovolts and located within the Harlem Springs circuit of the Cardiff substation, that it can handle an additional 2.7 megawatts of additional generation and 1.4 megawatts of new load. So the hosting capacity analysis is essentially, it's a snapshot in time that details how many kilowatts of DER generation and new load can be added at a specific node within the distribution grid. So this is a fundamental piece of information because it tells us where DER can interconnect so that it doesn't cause congestion, safety, or reliability issues. And the hosting capacity analysis also identifies the system limits to DER, such as thermal ratings, protection limits, power quality, which can include voltage, as well as safety standards. So it can help project developers design the best solution, as well as guide smart grid modernization investments that will enable the grid to accommodate greater amounts of DER. Now, the hosting capacity for a specific distribution circuit it's not a fixed value. It's a range depending on the DER technology or technologies added to the grid, as well as the exact location where that DER is sited. And this is shown below for a specific section of Pacific Gas and Electric's grid. You can see that DER listed on the left are both can offer generation as well as load, and you can see what those various levels are for those DER technologies or portfolio of technologies. And being able to proactively understand these limitations can help make the market operate more efficiently and design and size the right project with the right technologies at the right location on the grid. So the results of the hosting capacity analysis depend on a variety of factors. So for example, the location of a line segment often affects the hosting capacity. So a line segment near a substation can often handle more local generation than a line segment at the end of a long feeder. And that actually has to do with the physical limitations and thickness and gauge of those lines. The unique characteristics of a circuit's existing load profile, as well as its design, also is going to impact the hosting capacity analysis results. And as shown on the previous slide, different DER will be able to be sized differently. A solar profile is different than a solar plus storage profile, which is different than an EV profile. So all of these components together are going to alter the results that come out of that hosting capacity analysis. So hosting capacity analysis can be designed for various use cases. And I will just give a quick shout out to IREC, who really nicely laid this out in a recent report. Now, the first use case for hosting capacity analysis is to guide and inform interconnection of DER. And the second use case is to guide distribution system planning. So depending on the use case or cases desired, the hosting capacity analysis analytical process will vary a little bit. This includes what methodology will be employed, what levels of confidence, computational efficiency, spatial granularity, and other factors are going to provide the ultimate result for the specified use case. And just on a high level for the interconnection of DER, the way that that's been playing out in leading states is being able to have an iterative method that's a little bit more data intensive provides a lot more value and accuracy for the hosting capacity analysis results to actually sync up and be accurate with the interconnection process and ultimately be able to fulfill and serve as the interconnection process. For using hosting capacity analysis as a tool for distribution planning, that's more suited towards a streamlined method in which you're running various scenarios over time to see how policy decisions and investment decisions will impact the ability of the grid to reliably accommodate new DER under various scenarios. So hosting capacity analysis is already being implemented in a number of states, and those are shown here in red. This includes all of California's largest utilities, Pacific Gas and Electric, San Diego Gas and Electric, as well as Southern California Edison. We've shown a few snippets from their hosting capacity analysis. And so they've completed their first iteration and are right now working on refining their iterative methodology, which will be available in the summer of this year. And as they've worked through this process, it's expected that this next iteration will serve as the baseline for interconnecting or the interconnection process of DER in California moving forward. So states shown in orange are currently considering hosting capacity analysis requirements for utilities. So while there's still a lot of gray area on the map, there is kind of a growing movement and realization that hosting capacity analysis is going to be a core feature of what a utility offers in the future moving forward. And I would expect that this map will continue to turn color in the coming months and years. So let's move from hosting capacity analysis to the next component of distribution resources planning. So as part of the DRP process, utilities, regulators, and other key stakeholders work together to establish processes that fully and accurately value the benefits and grid services DER can provide. So this is a snapshot of some of those values that may be considered or included in such a methodology. And you can see that some values are customer specific, while other values are broadly applicable, like reduced CO2 emissions, local economic benefits, and energy security benefits through greater supply diversity. And for some of these DER values, location matters. Well-sited DER can reduce the need for local distribution upgrades, improve power quality and reactive power provisioning, and enhance the reliability and resilience of the grid. Importantly, DER can also reduce the need for new transmission-related investments. And as I recently mentioned, Long Island Power Authority calculated that spending roughly $20 million to incentivize the development of local solar in a constrained section of its grid would defer $84 million in transmission costs. So avoiding transmission-related costs needs to be part of this methodology and part of the equation. And there's no question that establishing this methodology is a truly complex undertaking with a lot of perspectives and stakeholders involved. But if we want to ensure that we're making the best investments into modernizing the grid, we need to start developing methodologies and refining them over time. So moving on to the third component of DRP, which are substation level pilot projects. So these pilot projects should capitalize on the opportunities uncovered through the hosting capacity analysis grid mapping, and they should test out the methodology to value DER. In essence, let's get a portfolio of DER on the grid at locations where we think they are most valuable and can save ratepayers money, and then let's learn from those demonstration projects. Was the hosting capacity analysis correct in terms of the grid's ability to accommodate this portfolio of resources? Was the value provided by these resources in alignment with the methodology and the projections that we had about the value of those resources? In this headline from New York City, caught a lot of attention because a $1.2 billion substation upgrade was proposed to meet needed, was proposed to meet projected load growth in Brooklyn and Queens in New York City. But Con Ed, the local utility, was able to defer this huge investment by contracting for 52 megawatts of demand reductions and 17 megawatts of DER investments, securing big savings for their ratepayers. And there are most certainly similar opportunities across the country in which DER offer a cost-effective solution to meet grid needs. And through the DRP, having demonstration projects that guide the identification and pursuit of these opportunities is a critical step and component of this process. And then the last component here is DER and load forecasts. So as DER transform the grid, we need to be planning and forecasting for continued growth of these resources. As I said, the grid's ever evolving, it's not static. So as part of their DRP process, utilities should be identifying various scenarios for DER and load growth based on various assumptions about growth rates and expected locations to understand how grid needs may change in the coming years. And then these DER and load forecasts, as a quick aside, can actually be utilized in the hosting capacity analysis for the use case that's focused on distribution system planning. So being able to take these defensible and well-researched forecasts, and be able to run models and projections about how those forecasts are going to impact distribution system operations over time in the coming years. So now that we've discussed the goals and components of DRP, let's talk a little bit more about the benefits of such a process, although I think I've alluded to that already. Nancy Lang, the chair of the Minnesota Public Utilities Commission, I think quite eloquently laid out her state's rationale for pursuing distribution system planning. So in Minnesota, they seek to maintain and enhance the safety, security, reliability, and resilience of the electricity grid at fair and reasonable costs, consistent with the state's energy policies. They want to ensure optimized utilization of electricity grid assets and resources to minimize total system costs. They want to increase transparency of utility investments and grid needs. They want to ensure distribution investments will achieve a flexible, resilient grid and meet customer needs under a range of futures. They want to create a system to evaluate cost-efficient non-wires alternatives to proposed investments, including DER provided services. And then lastly, they want to improve inputs for utility integrated resource plans. So these are certainly worthy goals every state should be pursuing. And in addition to these high-level objectives, there are some specific use cases for DRP. So the first one is it's to streamline interconnection of DER. And a DRP process proactively identifies the optimal sites for DER project siting, which can drive down project development costs and utility review time that they spend reviewing interconnection applications. So right now, the process for developing DER projects is backwards for the most part. Developers find a site, secure site control, design the project, and then submit the project to the local utility for an interconnection review process. Only too often to find out that their project site is not viable because interconnection costs are too high. So by proactively mapping the grid, we can significantly improve market efficiency. The hosting capacity analysis map drives the siting of local renewables and other DER to optimal spots on the grid, reducing project failure rates, driving down the cost of DER project development, and like I said, streamlining interconnection processes for both developers and utilities. And as part of this, the DRP process identifies available capacity, but also the constraints on the existing grid. What are those thresholds in which a line turns from green to red in terms of its ability to accommodate new DER? So projects can be thoughtfully and smartly designed to expand integration capacity through the use of storage or advanced or smart inverters and various technologies. So you're providing the market more information to bring the right solution to the table. And I will say, when Xcel Energy first went through their initial feeder analysis of its Minnesota distribution system, the utility found over 1,800 megawatts of available capacity within those feeders, and that's absolutely enormous potential. But when you dig into the data that Xcel released, you could immediately tell that renewable energy developers were simply shooting in the dark with their project siting. You could see a feeder that had a maximum capacity of 0.3 megawatts had nearly 20 megawatts worth of proposed projects on it. Yet there are other feeders that had multiple megawatts worth of capacity, but no projects proposed on those feeders. And such massive inefficiency in the development of local renewable energy projects adds substantial cost to the energy produced by these systems, because the cost of failed projects gets wrapped into the cost of successful projects. And here we're looking at a snapshot of PG&E's map, which details available capacity at the line segment level for PV. And you can see that box is checked color by PV IC. And through these hosting capacity analysis maps, we can streamline the entire project. So projects are sited at the right location where interconnection is quick and cheap and ease life for utility staff. So they'll have fewer interconnection requests to review. And through this grid mapping hosting capacity analysis process, interconnection processes can be streamlined and those resources driven to the best location on the grid. And the monetary savings of this proactive approach can be enormous. So this graph is from a May 2012 study by Southern California Edison that found guiding distributed generation projects can reduce their costs by more than 50%. So in this study, the lower costs were associated with the guided case, where 70% of the projects would be located within an urban area, and the higher costs were associated with the unguided case, where 70% of projects would be located in rural areas, significantly causing more transmission-related costs. So you can see in these two graphs, in that unguided case, the transmission component is absolutely enormous. It's greater than the entire cost for the guided case. So the locational methodology should certainly include transmission costs, but the DRP needs to inform and guide siting of projects in order to realize these savings. And the lessons from this SE study are indisputably true. PG&E has canceled 13 low voltage transmission projects planned in its service territory, and these projects were deemed no longer necessary in light of material lower load forecast levels since the projects were approved several years ago. And at a CAL-ISO board meeting, which is the California Independent System Operator, which is the transmission system operator in California, the PG&E's director of ISO relations and FERC kind of provided some detail about the project cancellation shown here on the right. You know, the need for those transmission projects is just not there anymore. We really appreciate the reappraisal of these projects. Load forecast has flattened in the service area from a combination of energy efficiency and rooftop solar, which eliminates the need for these upgrades. So guiding the deployment of DER close to loads within the distribution grid can secure significant ratepayer savings by avoiding transmission-related costs. And the value of avoiding future transmission capacity needs clearly must be considered, and DER procurement plans can and should be developed with the aim of deferring or even avoiding future transmission-related costs, such as I detailed in that Long Island Power Authority example. So in addition to streamlining interconnection and reducing costs of deploying DER, a DRP process also helps uncover where and what types of investments into the grid will provide the most bang for the buck. DRP creates a framework to evolve our investment strategy to maximize grid and ratepayer benefits by leveraging new technologies and approaches. And this quote here is from Pacific Gas and Electric's Distribution Resource Planning lead. He said, instead of looking strictly at wire solutions, we started looking at DERs as non-wire solutions and what the most cost-effective way of using them to meet our reliability, safety, and affordability standards. And this seems like common sense, but it truly is a new approach for the electric utility industry. And the DRP process lays the foundation to improve system planning processes by looking more holistically to identify the best solution to meet grid needs. So rather than looking at the impacts of individual DER through one-off interconnection review processes, distribution resources planning creates a framework to evaluate how DER fit together at the distribution system and transmission system levels. So we need to look across the entire system, identify what needs exist, and then look at the full suite of possible solutions, DER as well as more traditional investments. You know, and again, this is another quote from PG&E's DRP lead, but from a distribution planning perspective, DRP most definitely allowed for thinking that we haven't normally used. You know, and the intent of the DRP is to create a set of mutually supportive tools that detail how much DER can be deployed under a business as usual grid investment trajectory and build capabilities to compare portfolios of DER as alternatives to traditional grid investments. And what this graphic shows here is that DRP process truly does create that foundation to holistically evaluate options and devise sourcing for the best pathway forward. So when we talk about grid modernization, we need this layer of basic understanding to support smart decision-making about how to invest in the grid. And we need to understand the assumptions, the scenarios, the scope. We need to understand limitations and threshold limits on the existing distribution grid as well as its needs, and be able to evaluate options, both traditional investments as well as new innovative DER portfolios. Okay, so now that we've covered why DRP is necessary, its key components, and its benefits, let's talk a bit about the state of DRP policies in the US. So grid modernization efforts, either legislative or regulatory, are underway in the majority of states across the country. And this comes from the NC Clean Energy Technology Center. And as a breakout for this chart, you can see here, grid modernization is a broad term that covers many topics. But digging deeper into this research, we can see that in Q3 of 2017, there were 10 actions taken by states related to distribution system planning. And like I said, this is an upward trend that we expect will continue moving ahead in the months and years to follow. So of these 10 states, let's take a little bit of a state view of some of those leading efforts. So California was the first state to initiate a distribution resource planning process, which the Clean Coalition was heavily involved in. And the way that came about is we helped craft legislative language that was first introduced in 2011 and then again in 2012, before that language was picked up into AB 327 and passed into law in 2013. And this legislation directed the Public Utilities Commission to implement the DRP process, and the state's largest investor-owned utilities had to produce their initial distribution resource plans by July 1st of 2015. So California really embarked on this in the first and very comprehensive way. So it was kind of a long timeline from the first crafting of legislative language in 2015 to the first submission of plans in 2015. But the fact that this state and a number of other states have started to go down this pathway means other states can learn from those examples and implement a similar DRP process more quickly and more effectively. And the Clean Coalition wants to help accelerate the adoption of this policy in other states and leverage the experience and lessons learned in California to roll out DRP processes more quickly. So this grid matrix is from the DOE Grid Modernization Consortium Laboratory and provides additional insight into how various states are approaching distribution resource planning. So either through statutory, regulatory, or voluntary means, as you can see up top in those first couple rows, as well as what components these states are pulling into the mix, whether they're using hosting capacity analysis, a locational value methodology, and DER pilots as kind of alternatives to traditional wire investments. So what you can see is that there's a bit of a smorgasbord going on here across the country. Some states, like California and New York, have kind of the most robust processes, but various elements are being picked up, and more states will be added to this list and more boxes will be checked on existing states and new states as utilities, regulators, and other stakeholders continue to dig into these processes and truly understand the benefits of a DRP process and its foundational nature in this changing electricity landscape. So, and I'll briefly mention here that there's a few ways to get a DRP process moving in your state or utility territory. And those are through a legislative process, which is how California initiated its distribution resource planning process. It's also possible to bypass the legislative step and have state-level regulatory agency like a Public Utilities Commission or Public Service Commission, whatever that's called in your respective state, take the lead and initiate such a proceeding without that legislative mandate. And that's happened in Massachusetts and Hawaii and Maryland and Michigan. And the third pathway to initiate a DRP process is for the utility to just voluntarily embrace this process. And I think the leading example to date in the United States is the Sacramento Municipal Utility District, known as SMUD. And they've gone down this pathway and have a very strong and comprehensive distribution planning process that's playing out as we speak. And the growing volume of interconnection requests was truly a key driver for SMUD wanting to dig into distribution system planning and improve that process. And we'll say other utilities are starting to take some small steps forward voluntarily, which is great to see. But the transformation of the grid is underway. So the quicker and more comprehensively distribution resource planning processes are put in place, the smarter ratepayer dollars are going to be invested, because time is truly of the essence here, as investments are made nearly every day somewhere in the country. And I showed this graphic a little bit earlier, but it's worth circling back to because there are a lot of grid modernization efforts underway broadly across the entire country. And you can see all the states highlighted in blue there. So there may be ways to plug distribution resource planning as a component into an existing grid modernization process, whether it's about advanced inverters or advanced metering infrastructure or electric vehicles. There could be interesting opportunities to bring this content into that existing proceeding. And the Clean Coalition, as I said, really truly believes this is a foundational policy for smartly modernizing the grid to provide cleaner, more affordable, and more resilient power. And we want to help in any way that we can to get DRP processes initiated in other states across the country. So as I've said, we've been intimately involved in the creation of California's DRP, from the initial legislative language to guiding the regulatory implementation of DRP proceedings in California. And we've also supported the development of distribution resource planning in Colorado, where we worked on some legislative language last year and are now participating in a PUC open docket that's considering whether or not to formally open a distribution resource process in Colorado. And so we're an active participant in learning from the various lessons and pathways that these states are going down as they tackle this process. And ultimately, this is what we're working towards. We want to remove barriers to greater use of clean local energy, and distribution resource planning is truly an essential policy in achieving this goal. As Ben Franklin said, by failing to prepare, you are preparing to fail. Without a clear, transparent framework for understanding how to best invest in grid modernization efforts, the process will be lengthier and more expensive than it needs to be. So thank you for your time, and please follow up with me if you'd like to discuss distribution resource planning further or talk about its possibility or application in your state. And with that, I'll turn it back to you, Josh.
Thank you, John, for the excellent presentation. Very informative, and we've had a number of questions come in. So I'm going to read one aloud, and I have also chatted it to you in the chat box for you to read it as we go through them. So the first question is, are we ready to be able to do DER forecasts that are geographically disaggregated to predict DER growth by location?
Sorry, could you say that one more time?
Sure. Are we ready to be able to do DER forecasts that are geographically disaggregated to predict DER growth by location?
Yeah, I think that's a really good question. In kind of the state of modeling and analysis, I think it's still developing across the country. I think California, as some of our policy team, has been really active in the integration capacity analysis working groups to continue to evolve that process. I think there's still a lot of open questions, but the ability to both create defensible and perhaps somewhat accurate forecasts on DER growth, and then be able to use that for distribution system planning and consideration of policy impacts, technology impacts, that capability is definitely underway. So I hope that kind of answers your question at a high level. But if you want to talk more in depth about it, certainly shoot me an email and we can find some time to talk.
Great, thank you. The next question, you talked about the methodology to value DER. The source was the Newport Group. Do you know of examples in state PUCs or public utility commissions that have accepted this or a similar methodology?
Yeah, so yeah, really good question. The methodology piece, as I alluded to, I think is a very controversial piece. And there's a lot of stakeholders with a lot of various opinions on what should be included in that methodology and what shouldn't be included in that methodology. And then for the things that are included in that methodology, how do you value them? So I know that that's a process that has really kind of taken up a lot of time and energy in California specifically. But there is emerging consensus about what that methodology should look like. Again, it really kind of gets down into the weeds and details on the details of that specific methodology. And I think that that's going to vary state by state, exactly like we've seen valuation around net energy metered systems vary state to state in terms of what's included in that valuation approach. We could certainly dig up some resources around the current status of that methodology in California and be happy to share those with anyone.
Great, thank you.
Yep.
The next question, I believe that you answered in a follow-up slide, but it's worth going over a little bit again. And there's also a follow-up question that goes along with it. This one, it says, when you say, quote unquote, being considered for slide 23, which is the first map of the United States that you showed, what does that mean? And are there commission docket numbers associated with each state?
So slide 23, referring back to my notes here, is essentially that was a map of the United States with states that had officially implemented host and capacity analysis requirements for utilities in red, and then states that we're considering were listed in orange. That's kind of what that means. So states that like Colorado, for example, just to add some, I guess, color commentary to this, the PUC here is openly accepting comments and rules recommendations for what distribution resource planning could and should look like out here. So there's been no formal adoption of said process, but there is an open process underway to gather information, stakeholder input, so the commission can make a decision. So that's for states that are underway. They're still in that process of deciding what those requirements are going to look like and will they adopt them. In terms of docket numbers, yeah, there are docket numbers for at least a number of those states. I don't have those all at the ready, but there are some great tools online in which I'd be happy to chat with whoever asked that question to provide them some good resources to identify all those docket numbers. I do know a couple that I have in my notes, but not all of them off the top of my head.
Great, thanks, John. And just as a reminder, John and I will have your contact information for anybody who's asked a question that we didn't get to. So we can get back to you and have a conversation offline. Next question: what are the best practices for compensating DER owners for their contributions to the grid?
Yeah, that to me, it strikes me as a huge question, and I think one that's still very much being answered in various ways in different utility territories and in different states. I mean, just for rooftop solar, for example, you're seeing all sorts of approaches to valuing that, from traditional net metering at the retail rate to feed-in tariffs that compensate it at the avoided cost rate or at a above market rate price, or include a locational premium like we saw with LIPA. You're also seeing utility ownership of DG systems and various value streams associated with that. And that's really just for kind of distributed solar. So there's tons of different ways in which kind of value propositions are being tested and flushed out. And I guess in my opinion, I don't think it's a one size fits all for really any technology or any specific utility territory or off-taker for that, depending on what types of systems and what types of services you want from those systems, because that can also vary. There needs to be a program kind of developed and tested and refined before kind of rolling that out in kind of a full-blown way. And I think that's one thing that we're seeing with the DRP pilot projects is some really interesting and new approaches to procuring and valuing DER, like that Con Ed example. Being able to just essentially do a competitive solicitation for demand response. The utility is going to own a couple DER. There's going to be some third-party owned DER, and really kind of feeling out this space and seeing what's going to work the best in terms of being able to certainly secure these resources and their services, and then compensate for them in a way that's most cost-effective for ratepayers.
Great, thank you, John. I believe we have one or two more questions. How is residential solar considered in distribution resources planning? I am thinking of issues of reliability. And that second part is from the person who asked the question, not from me.
Yeah. So I guess I'm inferring when I hear residential solar that's referring to behind the meter solar systems. And so the way that these interconnection processes are done in various states have various interconnection rules related to net metered systems. The way that that's played out in California is this is actually providing some additional layer of proactive visibility around circuits, and particularly line sections within a circuit that are heavily saturated. So folks can know upfront, are there going to be issues around reliability related to that circuit and that interconnection of that system, and the utility can kind of get a proactive jump on that and know that in advance, as opposed to reactively receiving that interconnection application and then needing to go do this analysis and figure out are there going to be any safety or reliability issues. So it certainly ties in with it, but I think there's variability on how exactly the hosting capacity analysis interact with interconnection processes in various states.
Great, thank you, John. All right, this will be the last question for you. On slide 30, which was the SCE chart on system costs, the attendee asks, slide 30 makes the case for avoidable costs. In addition, though, the guided case could help generate vastly more avoided grid costs too, correct?
Could create vastly more avoided grid costs.
Yes.
I guess I guess if that's referring to the distribution system cost, then the answer is yes. I mean, so the guided case in that SCE example was related to Southern California Edison modeling the cost of meeting their share of what was Governor Brown's 1.2 gigawatt goal for distributed generation in the state of California. By guiding those DG projects to within the distribution system, you were able to avoid a significant amount of transmission related costs. And that's what that graph was showing. But I think the question is saying, wouldn't you also be able to avoid a lot of distribution related costs as well if you guided them through a hosting capacity analysis? And I would say yes. The answer is the more that you can proactively identify areas on the grid where capacity exists, within the distribution system, and know how much capacity is available, and the more you site projects towards that, the more that's going to drive down both transmission related costs as well as distribution side related costs.
Great, thank you very much. I think that clarifies most of it. We could, the person who asked that question, we can get back to you offline as well. Well, that takes us to 11:59. So I want to thank John Bernhardt for his presentation. And just as a reminder, this webinar was recorded, so we will be sending out via email a link to the recording of the webinar and access to the presentation slides itself. If you have any questions for John Bernhardt, please email him, and his email is on the last slide on the screen. It is john@clean-coalition.org. We have several other webinars coming up from the Clean Coalition. You can go on our website, clean-coalition.org, to upcoming events and see which ones are interesting to you and register there. So have a great day, everybody. Thanks for joining.